Okay, maybe I start. Is that, are we good here?
I think so. Yeah.
Um, okay, so today we will go over different things. Like I have 6 topics, small pieces, ready to go. One would be limit laws, one-sided limit, and then squeeze theorem. And the next one will be continuity. Um, what was it? Continuity intermediate value theorem, and one more thing I cover. I don't remember what was that, but so I will try to go a little bit faster at the beginning, so everything you have seen. Well, I'm assuming a long time ago. I will go a little bit fast, and the focus will be hopefully on the spots that you need more help for. Okay, so let me start with the limit. Well, the definition of the limit is that, well, we say that a function as f approaches to a has limit L if, well, when we have the graph of the function, this is a, and as we get closer to the values of x, so either from this side or from that side, the values of y, which will be, okay, something like for each value of x, we have a value for f of x. And as you go, you notice that the further we get closer to a from either side, uh, the value of that function, values of that function get approach or get closer and closer to L. Um, what is important here is that remark that when you're working with a limit, we always ignore the value of the function at that point. So while studying a limit of a function as x approaches to a, we ignore, this is the strongest word I can put here, the value of the function at a. In other words, studying limit is not about the value of the function at that point. While it can uh, be equal to the value of the function. But what is important for us is just the trend of the values of the function close to a. So that's something that you have to always keep in mind. F of a is not what we are trying to see. We are trying to see what is the value of the function. Well, with this definition, actually, the precise definition of limit is not easy. So you need to have some tools, some facts. So this is what is called limit laws. So, well, assume that we have two functions, and both of the limits as x goes to a exist. Then we can make new functions out of these two functions. For example, we can multiply f by a constant and then try to find the limit of that function. In this case, this will be c limit of f of x as x approaches to a. So that's the first thing. It's called constant multiple. And the second thing is, well, what if you're trying to find the limit of some of these two functions as x approaches to a? Well, this will be sum of limits of these functions. So as x approaches to a, as x approaches to a. The same goes with the, oops, the same goes with the, why this is not, okay. The same goes with the minus sign, subtraction, and the same goes with the product. So that's product rule. When it comes to the, maybe I should put like that so that you don't confuse it by x. And the importance, so this will be rule 2, 3, I'll write two of them at least. There's product and sum and differences. And then we have very important one, which is called quotient. Quotient law. It says, well, how about the limit of the quotient of f over g as x approaches to a? Well, this will work, will be quotient of limits as x approaches to a, as x approaches to a. Well, if I leave it like that, that would be a big lie. This is true only if limit of f of x, oh, sorry, the limit of the denominator is something non-zero. If that is zero, you see, I cannot put that number in the denominator. Zero in the denominator is a big, big no in math. So you cannot put zero in the denominator. That's why quotient law has this very important fact, and as you will see later in this session, that will generate a lot of new things for us. Okay, just having all these things said, let's just start doing some examples. I have two functions, f and g. I don't know what are these functions. The only thing I know is the limits of these functions as x approaches to 2 or x approaches to 1. And then the question is, what are the limits, the given limits? So here, I have sums of two limits. So first this guy and this one. So limit of f of x gx squared as x approaches to 2 plus limit of 1 as x approaches to 2. Oh, I missed a few more laws, but I will try to put them here as we go on. So then this is the product. So the limit of the first one and then the limit of the second one as x approaches to 2, as x approaches to 2 plus limit of 1 as x approaches to 2. And here, this is, you can either consider it as gx times gx, or you can consider another law, which is called power law. And this is telling me that this will be limit of f of x, limit of gx squared as x approaches to 2, plus limit of 1 as x approaches to 2. Well, the first limit I know it is -3 times the second limit is gx as x goes to 2. This is 2 squared, which will, and then plus. Last one is limit of constant. Limit of constant function, no matter what is a or what is the point that we are approaching to, this will be that constant. So basically what we found here is -3 times 4, that's -12 plus 1. The same kind of things works here. We have the quotient. Well, when you're working with quotient, you first make sure that the limit of the denominator is not 0. So limit of the denominator in this case is equal to limit, okay, I'm applying the sum and the product. So it will be limit of 1 as x approaches to 1 plus limit of x as x approaches to 1 and times limit of gx as x approaches to 1. So by this, you get 1 plus 1 times limit of the function as g as x approaches to 1 is 0. So this is 1. So you see the limit of the denominator is non-zero, then right away we can go ahead and do the quotient law. And from here, as we computed this, as we computed this guy, this is 1, so I will put 1 in down there, and in the numerator we'll get limit of x squared, that's power law, plus limit, this is sum law.
That is minus, by the way.
Oh, is it minus? Thank you. So that is a minus sign. I did put plus. Okay, this is good now. And this will give me, well, whatever I'm looking for. So 1 squared minus limit of function as x goes to 1 is 1 and over 1. So this is 0 over 1. Well, 0 divided by any number is a 0. Any non-zero number. Yeah. And this last one is called the the root law. It says that as far as you can put the final result under that square root or that root, you're good to go and just switch the root and the limit. Here, what you need to note first is that limit of the function under the square root as I apply all the laws here, I will get negative 3 squared plus 2 times, as x goes to 2, this is 2, plus 2 plus 1, yes? And this is 9 plus 4 plus 2 plus 1, and that is 16. When you have 16 like that, it is positive and it is a number I can put there, so that will give me the go ahead light and green light, and I can take the limit of the inside the root and then find root of that. So this will be just, so this way we without knowing what are f and g, we kind of can do apply all the rules and find the values that we are trying to find. Is there any question, any comments, Sinan, so far?
No.
Okay, okay. So something that will come up as what you will see in the next things is that, well, since you know that limit of x, so that maybe I write fact 1. This is easy fact to see. Limit of x as x goes to any number, this is equal to a itself. And fact 2 is that limit of x, constant, any constant, as x approaches to a is equal to that constant again, c's constant. And you see, these two and plus all the limit laws will give me two important things. Why did I put that up there? So this and that together will give me two important facts. One is, when you're trying to find limit of a polynomial, if px is a polynomial, meaning that, well, it is of something like this form, like we have some powers of n plus some other powers of n, all of the, each one is multiplied by a constant, and this will go up to a 1x plus a 0. Then you can combine these two facts and limit laws, and as a result, limit of px, any polynomial, as x goes to a, would be the same thing as evaluating that polynomial. And well, this is a very strong thing. It means that when it comes to the polynomial, evaluating and finding limit is the same thing. And also, if you have two polynomials and you have quotient of that, px, qx, then, and if q of a is non-zero, or p and q are polynomials, then in this case, we call these guys rational functions. Again, the rational function finding limit is the same thing as evaluating that function at that point. So this is PA, Q. Well, this has a meaning because you already know what is continuity. It means that all polynomials are continuous everywhere. And it means that all rational functions are continuous on their domain. So that's two things that you will come right away from that. Well, as a result of that, you will see right away, for example, these guys, limit of this will be 1 to the power 3 minus 4 times 1 plus 1, which will give me negative 2. Or this guy here, so the only thing I need to check is that in the denominator, 2 to the power 2 minus 3 times 2 plus 5, this is 4 minus 6, it is negative 2 plus 5, this is 3. So this is non-zero. So right away I can do substitute. That's what you need to, 2 minus 1, 2 squared minus 3 times 2 plus 5. And that is 1 over 3. And, well.
Could you scroll up a little bit? Someone is asking to see the last part of the note very quickly, but I don't know.
Okay, so let's do this thing. Sinan, if this comes up, please keep for later when I ask if there's anything. Yes.
All right, sure.
No, that's all right. That's all right. Because I'm trying to do the video recording so that I can use from these ones. And if there's no interruption between while I'm solving the questions, that would be nice. At the end, yes, you can go ahead and ask. That's good. Okay, how about this one? Okay, I know that the limit, okay, what is the limit of cosine x as x approaches to 0? Okay, see, you have to look at the graph of cosine x. And as you see, when I get closer to x, the values of function get closer to the value of the function at 0. Well, let me start from here, from there, from there, from there. And as you see, all of them getting closer to 1, the values. So that means that actually this is equal to 1. And limit of x cubed minus x squared plus 3 as x goes to 0. This is, you apply the root law, and knowing that under that root is polynomial, and I can just compute it by doing this, will give me root 3. Why did I do these things? Because this is now product of that, so it will be 1 times root 3, which is basically. So this way, you can combine easy facts from the limit, from the functions, easier function, and find limits of more complicated function. Is there any question, any comments seen on here I can?
No, we're all good.
Oh, thank you, thanks. So let's then go for the one-sided limits. The point of limit, so limit x approaches, so let me just write limits and one-sided limits. So the point here is that, well, first of all, when you're getting closer to A, you have to get closer to A from both sides. But you can restrict yourself only from the numbers less than A, or from the right or from the right. So this guy is that approaching to A from the right, from the left, which by the way means what? Means that we look for the trend of values of f of x for x's close to A and x's which are less than A. So we get closer to A only from the left. So we get closer like that. Okay. But when it comes to A, x approaches to A from right, that means that we are getting closer to A from the values bigger than that. So approaching to A from the right, or just using values of x which are bigger than A. And well, you may say, okay, so this is two new things, and well, there is an old one. What is the relation between these two? So that is given by another fact, a theorem saying that limit of a function as x approaches to A exists and equal to L if and only if the right limit exists, the left limit exists, and these two guys are equal to each other. So this has some nice implications, meaning that, well, to compute the limit, you can start with one-sided limits, compute each one, and then check if they exist and they are equal or not. Well, you may say, oh, who is so happy to, instead of using one limit, to use two limits to get the result? Well, this is specifically useful when the function is piecewise defined. So when it comes to the function piecewise defined function, and you're trying to find a limit of the function as x approaches to one of these separating points, domain separating points, you do the right, you do the left, and check if they are equal or not. Okay. So for example, well, right away that we have an example here. So I'm trying to find a limit of this function. This is piecewise defined function. That's the first thing you have to see. And we are trying to find the limit of the function as x approaches to -1 from left, from right, and it's sorry about that. So here, what we do is, first of all, we are approaching to -1 from the left. It means that we only considering values of x close to -1, but smaller than -1. On that part, the function is given by this equation here, x plus 2. So now you are trying to find limit of x plus 2 as x approaches to -1 from the left. But we know that this is a polynomial, and polynomials also always have limit. That means that the one-sided limit and two-sided limits for these guys are going to be the same thing. By this step, I get rid of that negative sign. Now you already know how to compute limit of a function which is a polynomial. So in this case, this will be -1 plus 2, which will give me 1. How about I do use blue so that, okay, so I got 1 there. How about values of x which are approaching to -1 from the right? So you see, we are approaching to -1 with values bigger than -1. You may ask yourself, well, oh, if something is bigger than 0, it will be bigger than -1. Should I take this one or that one? This is the point that approaching is going to be important. Yes, if x is bigger than 0, it is bigger than -1. But since we are only getting closer to -1, the values of x will be important, which are closer to -1. But if x is bigger than 0, it cannot get past the 0. So that means right away that, well, I should take that function. So limit of x squared plus 1 over x minus 1 as x goes to -1 plus. And okay, so that guy, again, I can turn that to real limit, two-sided limit. And from there, you use the facts that we said. So this is a polynomial, rational function, and you will have -1 squared plus 1 over -1 minus 1, which is equal to what? 2 over -2, which is negative. Okay, well, this guy, the left limit exists, it is 1. The right limit exists, it is -1. These guys are not equal. As a result, the function does not have limit. So the limit does not exist. How did you know? Because the left limit exists, right limit exists, they are not equal. I use the fact up there. Very nice. How about this point here down there? So we are getting closer to 0 from left, so we'll consider only this part. So that means that the function is given by, again, by that rational part, and left limit, right limit for rational functions at the given points are the same. And this is just evaluation because this is rational function. This is -1. So I got the left limit. For the right limit, so we will consider the right limit as x approaches to 0 plus, and the function in that domain is sine of 1 over x. Sine of 1 over x, this is only function that you have to know is not defined. So this guy does not have limit at 0. So this guy starts like this and goes down, goes up, gets crazier as get closer to 0, and doesn't approach to any number as we get closer to 0. It just oscillates even more crazier as we get. So this is from the right. From the left is going to be same story, and it gets bad and worse and worse. So limit of this guy as x approaches to 0 from the left does not exist. So now, how about the limit of the whole function? Well, limit of the whole function exists if and only if the right limit exists, left limit exists. Well, here, the right limit does not exist. So that means that this function doesn't have limit at 0. important piece is that if you have functions, piecewise defined function, and you want to approach to numbers which are on the domain, on the separating points of the domain, you should do the right limit, left limit, and then see if they're equal or not. Okay. Is there any question, any comments there, Sino?
Yeah, I was just answering it. So someone asked about sine 1 over x.
Okay.
Uh, it doesn't exist, and they ask if they supposed to know it, how to graph it.
Oh, how to, okay, so this is something. This is only example in this book that you should know how, based on the graph of this function, the limit as x approaches to 0 does not exist. You may say, okay, how do I know the graph? Well, look at this guy. Here I draw. That's what you need to know. Well, okay, sorry, I'm not a good graph
Something
sketch.
with your audio.
Pardon?
Something is wrong with your audio. There is this mechanical thing. So.
Oh, is it better now? Maybe.
Yeah.
Okay. Okay. So so probably I have to go from the beginning. Is that Sinan when that happened?
Kind of. I mean, the last few sentences were just.
Sure. Okay. See, sine of 1 over x, the function sine of 1 over x, it's good idea at this point you think about why the graph of that function is this form. Well, if you don't want to think about this, just look at the graph in the textbook, or use one of these.
It's happening again, by the way. I think
Game?
can others hear him well? Is it just me or?
He sounds a bit
Yeah.
glitchy.
Yeah. Others are
Oh,
also
okay.
having the same problem.
Okay. What can I do? Let me see. Is this still there like that?
Right now, it is good, but.
Uh-huh. Okay. You see, the only thing I can check is my connection, which seems all right. Okay, let me go ahead. Hopefully it will be gone. I don't know what to do if there is any problem. Okay.
Just right there, when you're explaining, it happened again, but I don't know. It's Zoom, so.
How about maybe I change okay, mic on. Wait.
You're muted. We can't hear you. You're muted.
How about now?
Now it sounds good to me.
Is it better? Hopefully, I don't know. But where did that sharing go? Okay, it is here. So you can see my sharing screen, yes?
Yeah.
So, yeah?
Yeah.
Okay, good. So hopefully it won't, I really don't know what if the internet doesn't work nicely for me, or what should I do then? So back to Muhammad's question. So sine 1 over x is something that we should know. At least look once, look at the textbook, and you try to make sense of that. If you can't, that's all right. But if you're asking me, do I need to know, sine 1 over x is important, and yes, better to at least see someone else's sketches. And see, there is a point here, domain of this function is everything but a 0. So that's why I try to put some point down there, meaning that what it is defined for all values when get closer to 0, but it's not defined at 0. Does that answer the question?
Oh yeah, it does. I actually just wanted to know if it's okay if we just assume that it's sine 1 over 0, because we just have to
No, Mama. You see, the domain, you cannot put 0 there. So this is one of the cases that that 0 is not in the domain, but we can still ask for what is the limit of function as x approaches to 0.
Okay, sounds good. Thank you. But in other cases, we would just substitute whatever the limit is.
No, never substitute. Okay, so the whole idea of all the things that I was explaining was that get out of that substitution. Yes, it will work for some cases, as we had up here. For these two cases, for example. Yes, it will work for those ones. But in general, substitution is not what it works. For example, in these cases, you cannot write like f of 2 times g of 2 squared plus 1. That doesn't make sense. Limit goes to limit. Product goes to product of limits. Well, okay, for different functions, there are different ways to find it. But in some cases, yes, it is substitution. But in general, no, substitution is not limit. Substitution is not limit. If you want to know the topic in the level of calculus 1000, just know it this way. Sometimes, yes, it is working just by substitution, but saying that limits always substitution, that's a big mistake. Okay, Sinan, is there any other question?
Oh, teacher, can you explain me again about the sign? This sign 1 divided by x, because I cannot understand why this function, this limit does not exist. I still cannot understand.
Okay, so let me explain it here. The function, why the function looks that way, I said, well, take time once and you will see why. But if you can't, this is what you should keep in mind. Sine 1 over x, the graph of the function, works this way. As you get closer to 0, it gets more oscillating and more oscillating. Check the book, textbook has better graph, but everything is that, okay, so if you send x to 1 over x, you're basically sending the interval 0, 1 to 1 to plus infinity. So the function sine x, which is nice like this piece, well, up to 1, which is somewhere here, up to 1 will be turned into this piece up to here. And everything else, so a little bit more explanation, hopefully it will be helpful. Everything else from 1 to plus infinity will go to 0. Oh, I cannot put 0 there. Open 0 to 1 goes 1 to infinity. So that piece goes there. And from 1 to infinity, whatever is from 1 to infinity goes to 0, 1. And that means that this part, the whole thing which repeats from here, you have to kind of fit in here. That's how it is fit there. And and you cannot do it just by looking at the function. You should either understand what is the graph of the function or know the graph of the function from somewhere. Okay, Sinan, is there any other question?
Yes, there's two. Multiple students asked about records of the course. Where and when will it be posted?
Okay, soon.
All right.
Soon.
And we're going to use OWL, right?
Yes, well, what I mean by OWL is that I will post it on my YouTube, and then from there I will give you the links on tutorial section. When they're done, at least updated 3 first weeks, I will send out an email, and then you will be able to go and check them. Okay, any other questions?
One is, can you explain how x approaches to -1 from the left can be the same thing as x goes to -1 for the first sub-question?
Oh, okay. Why did I go from this to that? Yes. Well, this is, okay, thank you. Yes, sure.
Yes,
You see, this is something interesting, that when you dealing with this function x minus what, when you're dealing with the function f here, then you have to be very careful what is left, what is right. But then when you put this x plus 2, this is now a completely different function. It is a polynomial, and we know that polynomials have limits. And a function, if it has limit, the right limit and left limit are going to be equal. That's why I changed the left limit of this guy, which is a polynomial, to the limit of that guy. I didn't change limit of f of x as x approaches to -1 to limit of f of x as x approaches to 1. That's not what I did. I saw what is happening for f on that interval, which was a polynomial. Now polynomials have limit, so left limit and the right limit or the general limit are going to be equal. That's how it works.
Oh, teacher, I cannot I cannot understand why the second function, like the limit, the x approaches -1. But I always think the sine 1 divided by x is also included in this range.
Piyong, I am going to ask another time. Please don't, if you have a question, you have to please send to the chat.
Okay.
And this is, okay, let me, I will try to. Sinan, could you please, there is a tick down there somewhere that if you pick it up, then they won't be able to do that. I guess I have explained a little bit more than I needed here. If you have question, please send me an email or sign up for a meeting, then we can go ahead and do check together. But for now, I guess I have explained twice and I will stop it there. Sinan, did we have any other question?
No, that was it.
Okay, thank you. So for this one, let's just do this one now. So here you say, oh, okay, we have absolute value of x plus 1. What is the absolute value of x plus 1? Well, absolute value of x is, if x is bigger than 0, then it will be just x itself. If x is less than 0, then I will need to multiply another negative sign to that guy such that it is positive. So it will give me always positive. Now I have x plus 1. You put all, for all x's, you put x plus 1. And as you see, absolute value of x plus 1 is piecewise defined function, x plus 1. If x is, I rewrite this guy as x bigger than negative 1. So this will be negative 1. And negative x minus 1 as x is less than negative 1. Okay, and then, well, I divide all sides by x plus 1. And in this case, x plus 1 over x plus 1. X needs to be bigger than equal to negative 1. I should be careful because at x equal to negative 1, this function is not defined. So I will just exclude negative 1 here at this step. And this guy would be minus, better to write as it was before so that I can show what is happening. So this is what we have now, divide by x. And this way, this is going to be 1, this is going to be negative 1. So we have a function which is piecewise defined, and negative 1 is the separating point. So if you're trying to find the limit, go by one-sided limits. So limit of absolute value of x plus 1 over x plus 1 as x approaches to negative 1 from the left. What does that give me? So here, since we are approaching to negative 1 from the left, my function will have the value negative 1 as x goes to negative. Well, this is constant. Constant, the limit of constant is that thing itself. How about limit from the right? So negative 1 plus x plus 1 over x plus 1. This will be limit of, so I have to consider this limit here, this function there, so that piece of the function this time, and this will be plus 1. Right limit exists, it is plus 1. Left limit exists, it is negative 1. These two are not equal. As a result, the limit does not exist. So that is what you will get for this. The limit does not exist. Again, at the beginning, you may see this thing as, okay, I need to do one of these limit tricks. But if you notice that absolute value function, absolute value is a piecewise defined, you will notice that the function we are studying is a piecewise defined function, and all the piecewise defined function, you have to go with the right and left limit format. Okay. Sinan, do we have any questions that I can answer?
I was just answering it. So first, could you explain the third step again, which is the part where he finds the piecewise function of, I think, absolute value of x plus 1 over x plus 1.
I see. Okay, you see, this is the absolute value of x. So let me just make a little bit less things here. So this is the absolute value of x plus 1. The function I'm interested in, absolute value of x plus 1 over x plus 1, is obtained by dividing this by x plus 1. It means that all the pieces that defines the function, you have to divide all of them by x plus 1. So the first piece is this one. I divided by x plus 1, which is the same thing. The second piece, which is negative x plus 1, I divided by x plus 1. And as a result, what we get is absolute value of x plus 1 over x plus 1 is 1, as x is bigger than negative 1, and it is negative 1 as x is less than. Does that make sense?
Does that, Mohammed? All right. says kind of.
Okay. Yeah, it's fine. It's kind of. Yeah, and the reason that I'm dropping that negative sign is that you see, I'm dividing the function by a function, other function, which is 0 at -1. So I will exclude that point, which is -1, because it's not in the domain of this new function. That's why I exclude. Are we good now? Can I?
I'm checking. Someone says, I'm confused how he got the value as the each one.
So x plus 1 over x plus 1, you're dividing x plus 1 by itself, it is 1. You're dividing minus x plus 1 by x plus 1. You're canceling these two, you get -1.
Someone says, what is the reason for dividing by x plus 1? It is how the function is defined.
This is what the function we are interested in, yes? Okay, that's why we divide. Okay, good. Is there any other series of questions or something?
I think we're clear.
Okay, good, good. Okay, here we have one question that you need to complete. This is based on a graph of the function. Sinan, could you please turn on that?
Sure. 90 seconds again?
Well, less. 1 minute should be enough.
All right.
Okay, how is it going?
Sorry, I was answering questions. So we have two B's, 24 D's, and two E's.
Okay, that's good thing. So just quickly for -1, well, you see the solid bullet is up here. So that means that f of -1 is equal to 4. For the limits, as we get closer to function to x from the left, so this is what we follow. This from the left is that way, and the graph is over there. And as you see, we get closer and closer to -1. For the positive one, we go closer when we go to -1 from the right. This is the graph of the function, and it gets down to 0. So this is not that, that is 0. Right limit is 0. The left limit is -1. These are not equal. So as a result, the limit as x approaches to -1 does not exist. So that is why this case is true. Should I stop here a little bit more or no?
I think we're good.
Okay, okay, good. So that same question has other that graph has other parts, but I would suggest to you screenshot this one and do it yourself, please. Okay. So the last topic of the first part is squeeze theorem. So what is squeeze theorem? Squeeze theorem says that you can use one inequality and two limits to find limit of a function. What is that? So if your function, well, it can be any crazy function, is bounded between two functions. So if this is function f, and then it is bounded between two functions like g and h. So let's say this is g, this is h. In other words, we know that for all values close to x, to a, this is what is happening. Well, all the values of this guy is less than that. And this is the point A. That's first condition. So that inequality we know is true. The second thing is that we know that the limit of the function bounded over a function from below as x approaches to a is equal to a number, and the limit of our function from the as x approaches to a for the function which is above is also the same number. So both of them get close to this number L. Then, as a result of, this thing, the squeeze theorem says that, well, limit of the middle function is also going to be equal to same number. So in other words, these two functions, upper function and lower function, if they have the same limit at a, they will squeeze f to the same limit as x approaches to a. That's where the name comes in. Sometimes in some books you will read it as the sandwich theorem. It means that the upper function and lower function will sandwich this f to the same limit as these two have at a. Key point here is you should make sure that the inequality exists, or you have an inequality and the limit exists. Okay? And they have the same limits. Well, you may say that, okay, you see, this is crazy. I am looking for limit of one function, but you're telling me, first give me an inequality and then find two limits. If they are the same, then you can find the limit in between of those two guys. Why should I do that? Why don't I go straight and find the limit of f of x as x approaches to a? Well, the answer is very simple. Sometimes finding the limit of the function in the middle is not easy. But finding the limit of both sides is easy to do. So that's why we kind of go ahead and find two easy functions here and there, and then use it to prove that the limit of the middle one is a number. Sinan, do we have question before I?
We're all good.
Good. Okay. So as an example, so here limit of.
One back up, by the way.
Pardon?
As soon as you said someone asked something, so did the three functions intersect? Which
okay, what is intersection? It means that they have the same value? Okay, as I said at the beginning, they may not have the same, they may not even be defined at that point. So they may get closer to each other as much as they can, but they may not have the same value over there. But if they are all defined there and they are equal, then they are continuous. Yes, that means like that. They will touch each other. They will intersect. But in general, that doesn't matter. So for example, GH can have the value of that guy up there. G can have that value down here. And F can be not defined at that point. Okay. So how about this one? Find the limit of x squared times cosine 1 over x. You say, okay, I know what to do. This is product of two functions. I found the limit of x squared as x goes to 0, which is 0. And then I found limit of cosine 1 over x as x goes to 0. What is that? Well, cosine 1 over x has very similar graph as the sine 1 over x. It will be crazy, what is called oscillating thing at around 0, and this one does not exist. If one of the multiples does not have limit, you cannot use the product rule. Product law. And not being able to use product law doesn't mean that the limit does not exist. It means that you have to find a different way. How do we do? This is where squeeze theorem comes in. We know that sine and cosine, whatever you put for that, is going to be a number between 1 and negative 1. Okay? Then I am interested in having x squared times cosine of 1 over x in the middle. So I will multiply both sides by x squared. So this will be x squared times negative 1. X squared times cosine of, well, here I said whatever you put, you can put 1 over x as well. So this is x squared times 1. And this will give me minus x squared less than x squared cosine 1 over x. And this will be x squared. Okay, now we got the inequality. This is the inequality we have there. Now, limit of the lower function as x goes to 0 is negative 0 squared, which is 0. Limit of upper function as x goes to 0 is 0 squared, which is 0. These two have the same limit, the inequality, and they have the same limit from the squeeze theorem. You right away conclude that limit of the middle one as x goes to 0 is 0. So we found the inequality. We found the limits of the upper limit and lower limit, and we show that they are same. Then squeeze theorem can go in right away and show that that guy is the limit of middle one is 0. Okay. Is there any questions, Sino, for this one?
Very good.
Very good. Okay, so here I have one question for you to do it yourself. Sinan, can we run the polls here?
I did it.
Okay.
How much time?
1 minute should be good. Well, maybe a little bit more than 1 minute, but just let me know when it is 1 minute.
1 minute is up.
Okay, how do we get, did we get?
We have 18 C's and 2 E's. And
Okay, okay, good. Okay, so here you see that we don't know what is f. So attacking this problem without knowing f, so finding limit of a function without knowing f has no meaning. Like, okay, what is f? But the information is given here is an inequality. If you have a function between two other functions, and we are being asked about the limit of the middle one, you should go right away and try to use squeeze theorem. Inequality is given. Limit of the left function as x goes to 1 is -1 square minus 1, which is -2. Limit of the right function as x goes to 1 is 1 square minus 4 times 1 plus 1, which is -2. The limit of the upper function is equal to limit of lower function as x is equal, as x approaches to 1. From this, squeeze theorem comes in, and the limit of the middle function, which I don't know what is that, it can be any function with that condition, is going to be -2, and that's why C is true. Okay, you can release the results maybe if they want to see.
I already started sharing the results.
Okay, thank you. That's nice. Thank you. Is there any question for this specific example?
Yes, someone really wanted you to scroll up a bit.
Like this much?
Is it what you missed, Edwin or Julian? All right.
Okay.
Yeah, we're good. So there are also 2 questions. First is when do we know when to use the squeezing theorem over product rule?
Over product rule. Well, there is no over. There is no hierarchy of product rule is down there. The squeeze theorem is up there. These will be just case by case. Always you start with the limit laws. That's a big thing. Okay, but as you saw, I intentionally tried to show you that starting with product rule is the first thing you should do. But product rule doesn't, or product law doesn't work in this case because one of the functions doesn't have limit. So you have to come up with new idea. For now, the new ideas we have other than limit laws is left-right limit and squeeze theorem. If you're asking in general, if in the wilderness of limits, well, that means that you have to practice a lot of things to be able to see when you can bring in. One of the important things for the squeeze theorem is that inequality. Finding inequalities is not easy. That's take it as a fact and hear from me. Well, in this specific case, well, it was not bad. You have to be able to follow this level of proving inequality. Or for this other example, it is already given. So in these examples, it's easy, but in general, not at all. Does that hopefully kind of answer the question? Okay.
Yes.
No, thank you.
And there's one more question. So after we find the inequality, do we take the functions without the middle one and then find the limits of them?
Yes. So you have to find the limit of upper one. Ignore the middle one. The middle one is the one you aiming to find its limit. Forget it. If you could have done without these inequalities, you should have gone before this. But it means that you now need to use the squeeze theorem. Squeeze theorem, when you apply after inequality, you find the limit of the function which is lower, limit of the function upper, forget the middle one. If they are equal, then squeeze theorem will give you the limit of the middle one. Is that good?
I think that's about it. I'm answering the last one, so, and yeah.
Okay. So now, Sinan, I noticed something. There is a chance that the way I set it up, I'm worried that it won't pick up my voice. So I am going to change again back to getting audio from my laptop. So if there is any issue, please let me know.
Sure, of course.
Okay, can you hear me now?
Yes, right now it's clear.
Okay, and the screen is up again, yes?
Yes.
Thank you, thanks. Okay, so the fourth topic, when the denominator is zero. So why we're discussing this? Because you remember when you're trying to find limit of a quotient as x goes to a, you can do limit of the numerator over limit of the denominator as x approaches to a, Well, this is a lie. This is not what we call quotient law. Quotient law is true only if the limit of the denominator is non-zero. What if the limit of the denominator is zero? So if limit of the denominator is zero, well, we cannot use quotient law. That's the first thing. If it is zero, we should forget quotient law. And then there will be two different possibilities. We try to find limit of the numerator. The limit of the numerator, if it is zero or it is a number which is not zero. Okay, so these two different cases can happen. Limit of the denominator was zero. Now, if the limit of the numerator is zero as well, then we say we have 0 over 0 in the determinate form. And what do we do here? Well, 0 over 0 is not the final result for us. 0 over 0 is just a middle step that tells us, screams at us, do something for me. What is that do something for me? We factor out the vanishing factor. What is vanishing factor? If x approaches to a, x minus a will be vanishing factor. So find the vanishing factor in both numerator and denominator, and then cancel the vanishing factor from the numerator and the denominator. You have to cancel from using those things, yes? And then when you cancel that, you will have another limit, which is quotient, and you can go ahead again, try to use quotient law. If it works, if it doesn't work, again, try to see which one of these cases happen. So that's when you have 0, limit of the numerator is 0, limit of denominator is 0. How about if the limit of the denominator is 0, but limit of the numerator is not 0? In that case, limit of f of x over gx as x approaches to a does not exist. Does not exist is very general word. We can, in these cases, we can go ahead and make it more precise. In this case, in particular, what we will have is we will have infinity limit. it will be either plus infinity or minus infinity. This is something that we will discuss next week. But just for now, if you get numerator non-zero, denominator 0, the limit does not exist, and it will be either plus infinity or minus. Okay? So this is the roadmap that you have to take when you're dealing with the quotients. First, try to use the quotient law. If the limit of the denominator is 0, you go ahead and compute the limit of numerator. If it is 0 again, you have 0 over 0 indeterminate form, and well, you need to resolve it by factoring out and canceling the vanishing factor. If the limit of the numerator is non-zero and the limit of the denominator is 0, then the limit does not exist, so it will be infinite limit. Okay, Sinan, can I move to the examples?
I think so, yeah.
Okay, thank you. So here, so this is the quotient. You wrote right away, you go to denominator and find limit of the denominator as x approaches to 1. Well, okay, so here, this is polynomial. This will be 1 squared plus 1 minus 2. This is 0. Limit of the denominator is 0. Right away, you go and conclude that cannot use quotient law. Okay, now that I cannot use quotient law, what should I do? Well, check the numerator. In this case, a limit of x squared minus 3x plus 2. As x approaches to 1, this will be 1 squared minus 3 times 1 plus 2. This is what? This is again 0. Yes? So then you can, well, now the numerator and denominator, both of them has 0 limit. So that means that our limit is an indeterminate form, 0 over 0. Here you should note something. I didn't write 0 over 0 in front of the equality. Why? Because 0 over 0 is neither a limit nor a number. This is just a middle step. It screams, do something. You cannot leave me alone this way. You should do something. And what is that thing that we have to do? Well, see, what is vanishing factor here? It's x minus 1. As I said, if x approaches to a, in this case, if x approaches to 1, x minus a is the vanishing factor. So we have to find the factors from the numerator and denominator, which are both x minus 1. So in the numerator, you have x minus 1, x minus 2. This is just factoring this guy. And in the denominator, we have x minus 1 and x, plus 2. And that is factoring quadratic. So if we factor numerator and denominator, and you see that there's a vanishing factor, you cancel them. Here, now you have a new limit. This limit is new one. So you should go from top to bottom, which is, can we apply the quotient law here? Yes, in this case, actually, you can apply because limit of the denominator is 1 plus 2, and limit of the numerator is 1 minus 2. That will give us minus 1 over 3. So this limit, after doing much of work, is negative 1 over 3. Do we have any question, any comments here?
Not completely material related, but someone's asking if we're going to talk about intermediate value theorem and continuity today, or will we?
Yes, I am going. We have still 40 minutes to finish this session, so wait a little bit. Be patient, please. Okay, so let me then go to the other example here. So I will do a little bit quicker here. X squared plus 2x plus 1 as x goes to negative. So I found limit of the denominator, which is 0. Limit of the numerator is 0. So this is indeterminate form. What is the vanishing factor? It will be x minus negative 1, which is x plus 1. So we are factoring numerator and denominator. This will be x plus 1, x plus 2. The denominator will be x plus 1 and x plus 1. You see, I can cancel these two, and what we will get now is a new limit, x plus 2 over x plus 1, as x goes to negative. This is completely new limit, so you have to go ahead and do all the things. But you notice that the denominator is 0. Limit of the denominator is 0. And limit of the numerator is what? 1. So I have 1 over 0. 1 over 0, you cannot write limit is equal 1 over 0. So if numerator is non-zero, the denominator is 0, the limit does not exist. If you want to know what kind of does not exist, it is plus infinity as x approaches to negative 1 plus. It is negative infinity as x approaches to negative 1 from the left. So that is something that we will discuss next time. But for now, when you see that, you say, okay, this does not exist, and go ahead and later to understand what is going on with the infinity limits. Are we good here?
Yep.
Okay. One more out of all these things again. So you go ahead and try to find the limit of the denominator. So let me just write this guy again. And what you notice is that, okay, limit of the denominator as x goes to 4 is equal to actually 0, yes? 64, that is, yes. So that is 0. Limit of the denominator is root 9 minus 4 plus 1 is 0. So it's 0 over 0. We should do with something with that. Okay. The denominator, you look at the denominator, this is cubic. Cubic is not easy to factor out, but if you factor 1x, you see there are x in all the terms, you will notice that, oh, this is now reduced to a nice, maybe I should do this in a different color so that you don't confuse it with, so this is what we have. So x times a quadratic, but now that quadratic I can simplify. So I can factor it. It is x times x minus an x something. Here, I'm looking for two numbers which add up to negative 5, and then you multiply, you get 4. That would be negative 4 and negative 1. In the numerator, we have rational function. When you're dealing with rational functions, it's not easy to factor out the vanishing factor. What you need to do, this is the first step, you should multiply that by its conjugate. Here, I will write, instead of minus x plus 1, I'll write minus x plus 1. So this way I have this guy. And then conjugate here is root 2x plus 1 plus x plus 1. And root 2x plus 1 plus x plus 1. And x goes to 4. Very nice. Now, in the numerator, we have a minus b times a plus b. That is a squared minus b squared, which will be 2x plus 1 minus x plus 1 squared. Oh, did I make a mistake here? Yes, I did. This is not minus x plus 1. This is minus x minus 1 because I am factoring negative sign there. So this will be x minus 1. This will be x minus 1. So in the denominator, we have x, the whole thing that we had before multiplied to this part. Now, see what is happening up here. Up here, this is 2x plus 1 minus x squared minus 2x plus 1. And if you write it down, you notice that the limit we are dealing with is now, simplify here. It is, I have minus x squared, and I have plus 4x. And 1 and negative 1, they cancel each other. So that's it. Now I can factor x from here. You get minus x. How about? So this will be x minus 4. So minus x, x minus 4, x, x minus 4, x minus 1, and then root 2x plus 1 plus x minus 1. Now you can cancel x minus 4s. Yeah. And from there, you have this new limit of minus x over x, x minus 1 times root 2x plus 1 plus x minus 1 as x goes to 4. And then this is quotient law. So you can use the quotient law, and this will give me minus 4, 4, 4 minus 1. This is root of 2 times 4, 8, plus 1 is 9, root 9 plus 4 minus 1. So this 4 cancels with that. I have negative 1 over 3 times 3 plus 3, which is negative 1 over 8. And that gives me the whole thing. Again, it started from the beginning. We got 0 over 0. To find the vanishing factor in the numerator, we multiply both numerator and denominator by the conjugate, simplified, factor out the quotient, the vanishing factor, cancel them. We got new function, new limit, and we applied the quotient law there. No, you don't need to know the quadratic in general, but quadratic like this, yes, because you can just factor out x as I showed you. Then this will be just, sorry, not cubic. I should have started from the cube. Sorry. You're not supposed to know how to factor cubic polynomials. But in some special cases like this one, you can factor out x and the remaining would be quadratic. So if you know how to do the quadratic there, then you just quadratic times x, you factor that. My laptop is dying, so I need to go get the charger. Sinan, can you take care of this few seconds? I'll come back.
Sure, no problem.
Okay, thanks.
In the meantime, Mohammed, you can ask it if you want, if it's easier to explain verbally.
I need something, David. Okay.
All right.
Okay, so basically my question is, when the professor multiplied with the conjugate, I thought that so you see how there's like two terms, like one in the numerator and one in the denominator. I thought one should be separate, like one should have a positive and the denominator should have a negative between them. Like shouldn't it be root 2x plus 1 plus x minus 1 over root 2x plus 1 minus bracket x minus 1? I could be like, I'm not
Sure.
100% sure, but I thought with
Sinan,
conjugates, one is
Sinan, can I answer
positive and one
that? Is
is
that
negative.
okay? I go.
Sure.
Yeah, thank you. So, Muhammad, see, when you're trying to multiply the rational function by its conjugate, this is what we know, yes? We need to multiply the numerator by this guy. Is that okay so far? You understand that that guy is conjugate of this one. So these are conjugate.
Yes.
So, but you multiply numerator by something, by some expression. We don't want to change the whole function. I have to divide the whole thing by exactly same thing that I multiplied to.
Okay, so it's just the opposite sign of what we're trying
What we have
to get the
originally,
conjugate
but we
of.
have to multiply the same conjugate both to numerator
Yeah.
and the denominator.
So the conjugate should equal to 1, right? If you know what I mean, like the right side, it's like 2x plus 1 plus
No,
x.
conjugate is that when you have root of some expression minus some other, the conjugate would be root of that. So this is conjugate. Root of that square plus circle.
Okay, got you.
So
I
here
understand.
it
Thank
is
you.
minus, we turned it to plus and then divided with the same thing so that we don't change it.
Okay, now it's clear. Thank you.
Okay, perfect. How about then I leave this one for you to do it yourself. You can take a screenshot right now if you like.
Anyway, we had another question,
Sure.
if we have time.
Yeah, quick one because yeah.
I don't know if it's going to be quick, but the question is, what happens if both numerator and denominator goes to infinity in the same direction?
We have not covered infinity limit this week. Well, in general, if this goes to infinity, like you're talking about infinity over infinity, that's another indeterminate form that you need to deal with it using different techniques. Yeah. So specifically, if you have polynomial over polynomial, you have to factor out the highest powers of numerator and denominator and then cancel. So that would be something that we will deal with next week in details. Okay. Oh, I have another one as well. Okay, maybe take a screenshot of this one and then. Sinan, is that okay? So can you take Sinan? Can you hear me?
Yeah.
Okay.
Can I take one?
Okay, sure. We have now one question that you should answer. This is the do-it-yourself question. Please go ahead and and try to do that. Could you please, Sinan,
I
release?
started it already.
Thank you. Just tell me when it is 1 minute. Because...
All right. We are up, but there's only a single answer. So
Okay, maybe leave it open and I will explain, see how this works. Okay, so this is a little bit tricky question. We have a limit of quotient And we know that it exists and is equal to E. Now, the question is, what is limit of f of x? So what we do here is that, okay, just think about this problem very single-mindedly. If this was something that I wanted to find the limit, I would start to check if the limit of the denominator is 0 or not. Yes. So this is 2 squared minus 3 times 2 plus 2. This will give me 4 minus 6 plus 2, which is equal to 0. So the limit of the denominator is 0. Okay? So from that, we know that there are two possibilities. Either limit of the numerator is 0 as well, or the limit of the numerator is not 0. I am claiming that the limit of the numerator is also 0. Why? If the limit of the numerator is non-zero, then in that case, it would be, the limit would be does not exist. But we know that the limit exists and it is equal to a number, E. Okay, so that means that this case cannot happen. What happens here is that definitely limit of the numerator is also 0. So limit of 2f of x plus pi as x approaches to 2 is equal to 0. If it is not 0 over 0, we are in trouble. It should be does not exist. But since we know it exists, definitely the limit of the numerator is going to be 0. As a result of that, since we know that the function has limit, we can apply the laws and the limit laws, and if this is L, we know that 2L plus pi is equal to 0. From that, we know that L is minus pi over 2. So that is why we have negative pi over 2. Do we have question on this one?
Nope.
Okay, so continuity. This is something that people were talking about, asking. So the definition of continuity has everything that you need to know, definition. So let me start with the definition. It says that f is continuous at a point A if this happens, limit of f of x as x approaches to A is really the value of the function at that point. What does this equality mean for us? It actually means three different things. First, it means that f is defined at A, and well, f of A makes sense. So we have value of f at A. The second thing says that what means that limit of the function as x approaches to A exists and it is equal to a number, is equal to a number like L. So the function is defined at A, so if A makes sense, the function, that limit exists at A. The third thing is that L, the limit, is equal to value of the function. So when it comes to checking continuity of a function at a point, you have to check three things in these three steps. F is defined, limit of the function exists, and the limit is equal to the value of the function. If the function is piecewise defined, well, to check that the limit exists, you should do the right limit and the left limit. You should make sure that They are, they exist and they are equal, and then that number is equal. Okay? Shall we go on this one? Why don't I have any question? Oh, I see. Okay. So the question says, find the discontinuities of the given function here. Okay. So I will go one by one. For values x bigger than 1, the function has this graph. The graph of function is continuous. It means that, well, at every point the limit exists and it's equal to value. So for x is bigger than 1 is continuous. For x is less than 1, so from this point on, it is again given by a continuous graph. So it is continuous. For anything between 1 and negative, oh, this is negative 1. Why did I miss that? Negative 1. For numbers between 1 and negative 1, it is the sine kind of function and it is continuous. Now, what about at x equal to negative 1? So you should make sure that you know, well, check all the things. Is f defined at negative 1? Or in other words, can you tell me what is f of negative 1? Well, f of negative 1, we actually did in one of the examples. This is 4. Sorry about that. So the first condition is there. Second condition, how about limit of the function as x approaches to 1? What you see from the positive side and negative side, they are different. So instead of checking that, I will check the right limit, which is 0. This is one of the examples we did before, so I can go a little bit quicker. And this is negative 1. These two are not equal. That means that limit of f of x as x approaches to negative 1 does not exist. The limit does not exist. It right away means that f is discontinuous at x equal to negative. Okay? How about at x equal to 2? Why did I do all these things wrongly? This is number 2. Here is 2. Here is 2. Sorry about that. So this will be, what about the point? So we will need to check all 3 things. First of all, value of the function at 2 is given by this, which is 1 over 2. So f at 2 is 1 over 2. The second thing, how about the limit? Well, the right limit of the function as x approaches to 2, well, you just look at this guy, this will go to 0. Limit of this function as x goes to 2 from the negative, well, it goes up to 0. So from this, you can conclude that the limit of the function, not the one-sided one, is equal to 0. Now, the third condition is that are these equal? So half is not equal to 0. So this is limit side, and this is f of 2. Well, the third condition fails. That means that f is not continuous at x equal to negative at 2, sorry. So that is another thing that you can see there, and just by looking at the graph. Sinan, is that okay? I move to the next example. If something comes up, you answer yourself. Is it?
I'm not sure about this one because it's about grading. So do they have to show all this work, or can they just write it intuitively in an assignment or an exam?
You should write enough information. It is not acceptable just by putting some spread out formulas, things. You should explain. If you may not use exactly the way, the notations I'm using, but you should make sure that you clearly mention what is the issue. If it's defined at that point or not, the limit exists or not, if all these things are okay, are they equal or not? So you should make sure, you can write by wording, but you should make sure that you include all these points there. Oh, this is actually one of do-it-yourself questions. Sinan, could you please run this one? And then we will start the other.
Can you guys see the polls? Because no one has answered yet. We're almost time.
Okay, then I will start. That's all right. That's good.
Right, we have two answers, so they're both D at this point. But
okay, let's see. Let's see. So we are trying to find values of A and B. So these are constants, such that the function is continuous everywhere. So let's see. On the values which are less than -1, the function is 2x plus a. Whatever a is, this is a polynomial, and it is continuous everywhere. In particular, it is continuous on values less than negative. This other one, well, on this interval, the function is this rational function. Yes. Rational function is continuous everywhere, but whatever makes the denominator 0. Here, the denominator is 0 at x equal to 1. So that is where this function has a problem. It's not continuous at x equal to 1. But note that x equal to 1 is not included here. So we can go ahead and write this is continuous on the given domain, which is this guy. And for this last piece, sine x over x, again, this is continuous on everywhere, but where x is equal to 0. But x is equal to 0 is not included in this part of the domain. So that means that it's continuous on all x is bigger than 0. Okay, now there are 3 points that we should check. 2 points that we should check, -1 and 0. For x equal to -1, we should see what is the limit of the function as x goes to 0 from the left. This is the same thing as 2x, not 0, -1. So 2x plus a as x goes to -1 minus, and we saw that this guy is equal to 2 -1 plus a, so minus 2 plus a. How about from the right? This is limit of x squared plus 3 over x minus 1 as x goes to -1, and that would be 4 over -2, which is negative. And from this, you see that, well, if the function is continuous, the limit exists. So if limit exists, then -2 plus a, the left limit, must be equal to right limit. From there, you see that a must be -2 minus -2, which is 0. Well, obviously, the value of the function at -1 is also given by this guy, which is -1 squared plus 3, -1 minus 1, which is -2, and that is good for us. Similar computation shows works for x equal to 0, limit of b sine x. Oh, okay, I should go step by step. X goes to 0 from the left of f of x. This is limit of x squared plus 3 over x minus 1 as x goes to 0 minus. This is 3 over -1, it is negative. How about limit of x goes to 0 plus f of x? This is limit of b sine x, b sine x over x as x goes to 0. Well, b is constant, and then limit of sine x over x as x goes to 0. So this is one of the important limits that we will learn in this course. Limit of sine x over x is 1. How you can prove it? It is one of the videos of week 4, and it uses squeeze theorem. So limit of sine x over x as x goes to 0 is 1. So b times 1 is 1. Left limit, right limit, and value of the function, which is -3, all three must be equal. So that means that b times 1 is the right limit. So -3 must be equal to b equal to -3. So from there, you see that we found the value of b. That's how we found that value. And hopefully this is something that now you can look at. Is there any question here? Can I?
We're good.
Okay. So now it's time for intermediate value theorem. Intermediate value theorem is very interesting result of continuity. So it says that let f be a continuous function on an interval a, b. It means that it is continuous everywhere between these two. At a, it is continuous from the right, and at b, it is continuous from the left. And so this is another condition. The value of the function at a is bigger than 0, and value of the function at the other end is less than 0. Or it could be the other way around. So either, so two ends have the value of the function at two endpoints have different sign, or f of a is negative and f of b is positive. So value of the function at 2 points, in other words, the value of the function is negative, is okay, at the endpoints have a different sign. One is positive, the other one is negative. So if you have these two conditions, continuous on the closed interval, and one is positive, the other one is negative. From there, IVT, intermediate value theorem, will tell me that there exists a root for f in the interval a, b. In other words, there is at least one point C in the interval AB such that f at C is equal to 0. So if you want to have some intuitive thing in mind, is that, okay, let's say this is AB, and the function has two values. The values of the function at two endpoints have different signs. So it's either like this or the other way around. Since the function is continuous, the function has to intercept with the x-axis. And intermediate value theorem says there exists such a thing. So that point is C. So if at one point the function is continuous and at one point it is positive and another point it is negative, there must be something at the middle or in between these two, such that the graph of the function intersects with the x-axis. Well, this is an interesting result because we can use it to show that some equations have solution. How do I go from the equation to function? Because intermediate value theorem was about functions. Now you give me an equation. Well, this is how you do. Make a function out of this equation. What is that function? Bring everything to one side. So it will be x to the power 5 minus 5x to the power 4 plus 1. Okay? Set that guy to be your function. Now, a root of this function is a solution for that equation. That's what it takes to go from an equation to a function. Okay, now conditions. F is continuous everywhere, in particular on the interval 0 to 3. That's the first thing. F of 0 is 0 to the power 5 minus 5 times 0 to the power 4 plus 1. This is 1. This is positive. F at 3 is 3 to the power 5 minus 5 times 3 to the power 4 plus 1. So this guy is 3 times 81 minus 5 times 81 plus 1, which is, okay, I can factor out 81 here, and that will be 3 minus 5, which is minus negative 2 plus 1. This is 100, negative 162 plus 1, which is negative 161. And this is a negative number. That is positive, that is negative, and function is continuous. IVT says, implies, there exists number C in the interval 0 to 3 such that f at C is equal to 0. Well, f at C is equal to 0. 0 what means what? Means that C to the power 5 minus 5 times C to the power 4 plus 1 is equal to 0. But from that, we get C to the power 5 minus 5, C to the power 4 is equal to negative 1. And that is the solution of the equation. Sinan, are we okay there?
Yep.
Yeah. So I have another example. I will just give you the main hints here. So here again, you define this function, sine x minus 2e to the power x minus 1. Show that f at -1 is actually a negative number. And f at, okay. So the question says that, can we use IVT to show that this has a solution? The answer is no. And when you check the conditions, you will see what is wrong. This is a good function. It's continuous everywhere, specifically -1 to 1. But when you evaluate, you will notice that this doesn't satisfy the conditions of IVT. So IVT cannot say that this equation has a solution. Actually, this equation doesn't have any solution. So I will leave this one as a question for you. So if you want, you can take a screenshot at this point. Okay. And this is very last thing. I know we are over time, but let's just finish this one and then go calculus free for this week. Sinan?
I have.
Thank you.
One minute is up, but do you want to give some more time?
Let me just go ahead and explain one by one better.
I'll leave the polls open.
Thank you. Thank you. So, okay, the question says find the true statements. There are 3 statements, 1, 2, 3. My claim is that all 3 are false. And I will give you examples for each one, counterexamples for each one. What is wrong with the first one? The first one says that the function is continuous on open interval AB. You see, IVT says that function is continuous on the closed interval AB. That's the difference. And well, that actually matters. And as I will show in this example, the function f of x is x, for x is less than 0, it is -1. For x is bigger than equal to 0, it is 1. Okay. Now, the function is continuous on the interval, open interval, -1 and 0. Yes, because well, on the -1, 0, the function is -1 and it is continuous everywhere. And well, f of -1 is -1, which is negative sign. F of 0 is 1, which is positive. But this function is never 0. It's either 1 or -1. Indeed, if you look at the graph of this function is like this. It never intercepts with the x-axis. So that means that this statement is wrong. That's a counterexample for that first statement. The second statement is wrong because you see, it says the function is continuous everywhere. That's nice. But the value of the function at two endpoints are negative. So f is continuous. It is continuous everywhere. So it means that in particular, it is continuous on the closed interval. F of A and f of B are negative. Can we conclude that this function has no root? Can we conclude that? Well, this is wrong. You see, what you may think is that, okay, this does not satisfy conditions of IVT. But something doesn't satisfy conditions of IVT, it doesn't mean that it won't have any root between those two. Matter of fact, the only thing you can say is that since it doesn't satisfy the conditions of IVT, we cannot use IVT. But the function still can have zeros in that zero roots in that interval. For example, consider like function f of x equal to minus x squared plus 1. And the interval, take it as a negative 2 and 2. It is continuous on this. F of negative 2 is negative 3. F of 2 is negative 3. But if you look at the function, this is our friend, parabola, yeah? In the interval negative 2 and 2, it has two roots, negative 1 and 1. Okay, so this is a counterexample of what it is said up there. The function has negative values at two ends. We cannot use IVT, but there might be other facts somewhere else living out there, which makes this guy some roots on that interval, which is this case, and this is counterexample for that. And the third thing is that, okay, the IVT says that there exists at least one root. It doesn't say it has exactly. So that is where this problem comes in. Example for this one, counterexample is easy. Counterexample is, for example, take sine x on the interval negative 3 pi over 2 and 3 pi over 2. This is positive on one end, negative on the other end, but it has how many roots? You see, I can sketch the graph of this guy. We'll go like that, and then go up like that. It has one root, two root, and three roots on that 3 pi over 2. That is negative 3 pi over 2. So this is a counterexample for that one. So IVT doesn't say it has exactly one root. It says at least one root. And that's why this is wrong. Okay, I guess this is what we have for today. Again, I am over time. I'm so sorry about that. I am working hard to not happen, but it seems that I should work a little bit more. Sinan, is there anything that we should address before we leave?
I think I answered the question. So
Thank you very much. Thank you. So if you don't have any question, thank you for attending the class and have a great night or great, I don't know, morning, whatever is working for you. You're welcome. You're welcome. You too. Oh, Sinan, you're writing that. Sorry, I don't.
Thank you. I mean, you too as well. But so